This week we're going to be identifying an unknown metal using the ideal gas law and by finding its molar mass. So the ideal gas law we haven't really talked about just yet. There are some simpler gas laws that I'm going to talk about in a second, but there is a general equivalency that we can write, which is PV equals nRT. So these are some variables. R is actually a gas constant, so it is constant, and its value is 0.08206 liters times atmospheres per mole times Kelvin. So it has kind of a bizarre set of units, but it will make some sense once we look at the other variables in this equation. P is the pressure. The pressure is in atmospheres in this particular setup. We are generally under about 1 atmosphere of pressure. That can change just a little bit, but that's where that unit originates. There are other units of pressure that we're not really going to talk about for a little bit, but we can interconvert between units of pressure as well. Volume is V. That's going to be in liters if we're using this particular gas constant. N is the number of moles of gas. It's very important that we are referring to number of moles of gas. We can't use this for anything besides a gas. It's an ideal gas law. So you may be tempted to use moles of something else, but it has to be moles of gas. T is the temperature in Kelvin. Again, we can see that because of our gas constant, we need to have temperature in Kelvin. If you were to plug all these variables in, you would see that these are equivalent if we were using this particular gas constant. There are other gas laws that we can get from the ideal gas law if 2 of those variables are kept constant. Those are the simple gas laws that I'll talk about in just a second. But they really all do derive from this ideal gas law. And we'll talk about it more in class, in your lecture class in the future. If we know 3 of these variables, we always know the gas constant. So if we know 3 of these variables associated with a particular gas, we can always solve for the 4th variable. And that's one of these ideas that we're gonna deal with in this lab. Lastly, something that is fairly bizarre that will also be needed for this lab is called Dalton's law of partial pressures. What it means is that if you have a mixture of various gases, the sum of the individual partial pressures of those gases will be the pressure total that we're referring to. So one example of this is the pressure that we're under right now is about 1 atmosphere, but we know that air is a mixture of many different gases. So most of it is nitrogen, then we have oxygen, and we have other minor gases like carbon dioxide or argon. So the sum of all of those pressures from those individual gases needs to equal the pressure total that I'm experiencing right now, which is roughly 1 atmosphere. So since most of the gas is nitrogen, roughly 78% of it, that means the partial pressure of that nitrogen gas is about 78% of the pressure total. So if I'm under 1 atmosphere, that would be 0.78 atmospheres would be the partial pressure associated with nitrogen gas that I'm currently experiencing. This will maybe make a little more sense as we move forward, but that is Dalton's law of partial pressures. So here we can take the ideal gas law and we can break it into these smaller, more simple gas laws called Boyle's law, Charles' law, and Avogadro's law. And really this is just the ideal gas law, but we are taking 2 of the 4 variables and keeping them constant. So for example, with Boyle's law, we are keeping the number of moles of gas constant and the temperature constant. So we're just seeing that there would be an inverse relationship between pressure and volume if we were to do that. I'm not going to spend much time on this, but these are all derived from the ideal gas law. And again, we'll talk more about this in the future, but for this lab, not terribly important. But if you hear these specific gas laws, they really are still a part of the ideal gas law, but they have some historical significance because they were determined beforehand. So in this lab, we're going to be collecting gas over water. The particular reaction that we'll be doing is we'll be taking some metal. In this particular example, we have zinc metal that's being dissolved in hydrochloric acid over on the left-hand side there. And it's releasing hydrogen gas. So here we see in this reaction, we're releasing hydrogen gas. We had zinc metal and hydrochloric acid that were dissolving together. You form this zinc chloride that's aqueous, and that will stay in your reaction vessel. So let's say we're dissolving the zinc metal. Hydrogen gas is moving up and through this tube, and it will be collected in some sort of vessel. And that vessel, we will be able to measure its volume. What's interesting about this is we are collecting that hydrogen gas mainly because we have a balanced chemical equation here. So if we can figure out how much hydrogen gas we produced in this reaction, we can actually backtrack that to how much zinc there was in the beginning. You could weigh that zinc, and based on doing some stoichiometry, you could actually figure out the identity of that metal. Of course, here it's zinc, but in this lab, we're going to have an unknown metal. There's going to be 3 different unknown metals. And we'll be using this to figure out the identity of that unknown metal using stoichiometry. So we're going to need to figure out how much gas is produced, hydrogen gas. One of the problems with this is that in this vessel, you don't just have hydrogen gas. You have also some water vapor that's in there. Okay, so just because water, and we're familiar with this, just because, humidity would be the analogy here. So we have some water vapor, depending on the temperature, floating around in here as well. So instead of this just being associated with hydrogen, we are also going to be having water in there as well. So gases are often collected by this displacing of water in some sort of container. Like I said, because water evaporates, you're also going to have some of that water vapor collected. So the partial pressure of the water vapor luckily only depends on the temperature of that water. So we can actually account for that pretty easily if we know the temperature, which we do, which we will know. And we can find out that by looking at a table, what the partial pressure of the water will be. So here's an example of that table. When the temperature is quite low, you can see the temperature being quite low here, temperature 0 degrees. The partial pressure, this is in millimeters of mercury, which is another unit. 760 millimeters of mercury is equal to 1 atmosphere. So this is a very low partial pressure, meaning very little water vapor is above that vessel when you're at 0 degrees Celsius. But we're often going to be closer to maybe 20 or 25 degrees Celsius, which is more like room temperature. And here you can see we have maybe somewhere between 17 and 24 millimeters of mercury associated with that water vapor. So that will be the partial pressure of water at that particular temperature. And we'll be able to use Dalton's law to then determine how much hydrogen gas was in that vessel. Okay, so if we collect a gas sample that has a total pressure of 758.2 millimeters of mercury, which again, that was about 1 atmosphere, which was what we would expect. And let's say it's at 25 degrees Celsius, the partial pressure of water vapor would be 23.78 millimeters of mercury. So we can use that to determine what the partial pressure of that dry hydrogen gas would be, and that would be 734.4 millimeters of mercury. So we can take that total pressure minus the partial pressure of water, and that will get us the partial pressure of hydrogen gas. This is the pressure that we would now use in our PV equals nRT in order to then find out these other variables. Okay, so here's our setup once again. We need to be careful with PV equals nRT. We have to be careful because the pressure that we're referring to sometimes is the pressure total, and that would mean that we're referring to the total number of gas molecules. which isn't really what we're interested in. We're really interested in the number of hydrogen molecules, the moles of hydrogen gas. And we can only get that if we have the pressure, the partial pressure that's just associated with hydrogen gas. And we can get that with this equation, which is what we had just talked about. This is Dalton's law. So the pressure total is roughly 1 atmosphere. We can subtract out the partial pressure of water based on that table and based on the temperature to solve for the partial pressure of hydrogen gas. This is the pressure that we would then be using in this equation to figure out these other variables. We would know, let's say, the temperature. R is the gas law, or a gas constant, so we will always know that. And the volume of the container will be measured. So we'll have all these other variables, and we can use that to figure out the moles of hydrogen gas. Like I had briefly mentioned before, we can then backtrack. Once we have the moles of hydrogen gas that were produced, we can backtrack and figure out the molar mass of the metal that was used. We'll have the mass of the metal. We can use stoichiometry to figure out the moles of the metal, since we have the moles of the hydrogen gas, and we'll have a balanced chemical equation. And that will be how we figure out the molar mass of our unknown metal. And with that molar mass, we can use that to identify which metal it is we had started with. Okay. This is essentially a diagram of the entire thing. The writing might be a little bit small, but I think you get the idea. You can pause the video and take a look more specifically at this. But this is going through some of those actual calculations and doing this, doing a reaction like this. Okay. Here we are going to have 3 different unknowns. Of course, since we're not in the lab at all, we have to give you some of these measurements. So we weighed out. So this is data for unknown A. The next 2 slides are B and C, and you will be assigned a particular unknown. But just walking through the data for unknown A, we would have weighed out the mass of the metal, and here's the mass of the metal for the 2 trials. And then we will have a volume of gas that was collected in milliliters. You're going to have to end up filling in the rest of this table. For example, here's the barometric pressure, this is the pressure total. And this is inches of mercury instead of millimeters of mercury. You can convert between inches of mercury and millimeters of mercury, just the same way you would convert between inches and millimeters anyway. And we can use that eventually to get to the atmospheric pressure. Okay, here we have the temperature in degrees Celsius. We can convert that to Kelvin. Here's vapor pressure of water. We had discussed how we would go about getting the values of vapor pressure for water. That was based on the table. We can then get the corrected hydrogen pressure just for the hydrogen gas, which was the pressure total minus the vapor pressure of water. We can correct that to be in the correct units for atmospheres. And then this is our value for our gas constant, which is a constant, so we can just record that value. We can use this ideal gas law now to get the moles of hydrogen gas. Again, if you're going to get the moles of hydrogen gas here, you must have the partial pressure of hydrogen gas, which will be these. We can use then stoichiometry to get to the moles of unknown metal. And then, once we have moles of unknown metal, and we have grams of unknown metal, we could get grams per mole. This is the molar mass of the unknown metal. We'll average that and see if that will be close enough in value to getting something, to identifying what that unknown metal's identity is. And that's what we'll fill in at the very end. So this was the data for unknown A. Here is the data for unknown B. Here is the data for unknown C.